Hi everyone, my name is Chiri, and today I will be speaking about dynamic pricing, especially with the focus for e-commerce, but it will be useful for SaaS products, B2C, and so on. But the main focus is going to be, let's say, smaller deals or smaller sales, and plenty of sales. So you might need a lot of data to do things I will be speaking about. Uh, in a minute about me. I am a founder of a software development company called Flexiana. I've been programming all my life, practically started as a child. Since the university, I have been in mathematical optimization, not machine learning. It was more operations research, which is more focused on, uh, let's say, optimizing logistics, optimizing manufacturing, and so on, without using neural networks, more using, let's say, simpler but still applied mathematics. About 15 years ago, I have got involved with the first project in the real world that was focused on a similar thing to this. It was in e-commerce, and it was, let's say, an algorithm to do personalization for a quite a successful portal, one of the biggest in the Czech Republic for Groupon loans and deals and so on. It was a lot of maths. You might not realize it, but actually personalization requires a lot of computing power. So there has been a first project in machine learning field. Also, more than 2 years ago, I started working on LLM apps. During those years, I worked as a CTO in a couple of companies. I was a consultant. I'm not consultant anymore. I was a mentor in a couple of startup accelerators. Now what I do is basically I'm building with my company. We are building various applications, products, etc. So what are we going to speak about today? So first, in a minute, I would like to explain why should you care about dynamic pricing. I think it's for many of you it might be obvious. And then we will get to Bayesian optimization and why Bayesian optimization is a good fit for dynamic pricing in e-commerce, SaaS, those situations. What are the possibilities? We will be speaking how to implement Bayesian optimization, dynamic pricing. I have some examples. It is a source code. I don't want to push you to be developers in this meeting. You should get value from this, even if you are not developers. So it will be like super quick, super brief, just to show you that it is doable. Many of those things are doable in hundreds of lines of code, can be developed quite quickly. Okay, so let's begin. So what's the reason for dynamic pricing? When you look at let's say, growth of, let's say, in e-commerce, for example, usually those companies start with, let's say, they have just a margin. So let's say, okay, we will purchase products from vendor, we will add 25%, 20% margin and start selling it. This is super naive way how to do it, but for many companies it works. And if you have good marketing, if you have optimized logistics, you might get pretty far with that. I know companies that have revenues on a scale of $40 million doing just this, and no applied mathematics, nothing, no operations research. So good marketing can get you pretty far. But at that moment, still, when you are on this scale, if you had dynamic pricing, you could easily raise or increase your profits by tens of percent. And on the other side, you have company like Amazon, which is the biggest beast in the world if we speak about dynamic pricing. They modify prices of 2.5 million products per day. So every second they modify prices of some products and brings them, let's say, an increase in $1 billion. At their P/E ratio, it added tens of billions to their valuation. Now, and what they do, like the biggest players, what they do, all the maths are available, all the libraries you need are available. So it's quite possible to implement those things yourselves. Of course, if we speak about Amazon, they have a team of data scientists that are constantly improving their models. You don't need to have such a thing, but there is always a chance to significantly improve profits by understanding how to, let's say, raise your prices or when to lower your prices if you can reach scale. About one quarter to one third of UK EU businesses in e-commerce are already using dynamic pricing. The dynamic pricing might be, let's say, more simplistic. Usually how it works is that you use decision-making trees. So you start with the original price of the product and you say, okay, let's add margin 20%. So if there is now, then, for example, read prices of your nearest competitors who provide similar level of customer care, etc. Try to have about the same price or maybe to be 1 cent lower. Then often there are additional filters like let's say changing the price to continue. So from $10 you turn it to $9.99 or $9.95. And that's it. So it's an algorithm that goes like a tree where you go step by step, but you sometimes might branch. For example, if it is possible to be cheaper than the customer and still keep your margin or not. So if it is possible, let's go this way. Otherwise, let's go that way. The payoff or the way how it pays off, it's usually a very good investment that pays off very fast. It depending on a number of your units, let's say your products that you are selling. So these are real numbers I found in the market. So it's quite common to see lift in revenues on a scale of, let's say, 8%, which if you look here, each percent in the price increase might add 8 times more increase in your profitability. So dynamic pricing is, but now we speak about generally dynamic pricing. We are not speaking yet about Bayesian optimization. So just by adding some dynamic pricing, you can improve your profitability by, let's say, 40%. And it pays off in a couple of months. So for many companies who are not there yet, they are growing, they have plenty of sales. The payback is in a couple of months. Now let's speak why Bayesian optimization. So the problem is, especially when you have, for example, a lot of products you are selling, the most common approach is based on grid. So you have an algorithm that's trying to increase the price, lower the price, increase the price, and it is scanning your demand for the product. And usually you ignore additional attributes. So for example, so you need to do this grid optimization. On average, you need 250 data points. And those data points might be, for example, successful sales. So imagine those millions and millions of purchases you need for, let's say, if you have 100,000 products. When you look at Bayesian optimization, there is a study we can add so this is recorded. Later we will put it on our YouTube channel as well. So we can put the link to the study. But the study shows that Bayesian optimization, which works completely differently, and I'll explain it today, needs just 1/10. So if you have, let's say, a big operation, a big e-commerce store that has millions of views. Still, using this classic grid-based optimizations will take you easily weeks to get all the learning done. And and what is great when you do dynamic pricing is basically that you have certain attributes about those customers, like whether they are using iPhone or Android or desktop computer, if they are coming to your website from this country or this location or that location, if they are like a customer who already purchased something or it's a new customer, if the source is from some comparison engine like Google Shopping or PPCs, etc. So all of those things are attributes. And for each combination of attributes, you need to do the training again, more or less, which means that if you have three attributes, you have like 1, 2, 4 times. So here, if you need 250 data points for grid base, it's you need 2000 cells to train the model on with three attributes. If we speak about Bayesian, it's just 1/10. So it's much faster, much cheaper. It helps you to evolve your models significantly faster. So this is the biggest advantage. Personally, I think that Bayesian optimization, Bayesian models are criminally underused in e-commerce and in optimization of manufacturing, logistics, marketing, etc. And now, for the Bayesian optimization, how it works. Now, we will be a little bit mathematical. I'm sorry for that. I promise I'm not going to show a lot of like source code, but I will try to explain you how it works, the whole thing. So, so when you do the optimization, you need like to go from point where you have like, for example, static margin, let's say 20% to the point where each customer is getting the highest price the customer is willing to pay for the product, right? This is increasing your margin. And so what you need to do first, you need to start with some good estimate. So when you have an e-commerce store, a good estimate is the current price. Uh, so actually, with Bayesian systems, you can start with random number, and it will quickly iterate towards a good number. But you might be, for example, starting with too high price or too low price. You might sell a couple of products too cheaply and completely undercut your margin. So it's actually good if you already know what might be about like the middle price that would work for majority of customers, which and it's a good thing. Most companies that have, let's say, e-commerce stores, as I said a couple of times already, the same thing can be applied for SaaS products or any situation where you can give different customers different price for your product. Um, so you start with this prior knowledge, and then you are constantly trying to provide different prices, a bit higher, a bit lower. And I will explain how this is happening. And every time the customer either buys or does not buy, you use this to train the model. So you enrich the model, and next time it is more accurate. So if you feed it with the parameters, like let's say, okay, this person is visiting your e-commerce store from iPhone. He's located in Los Angeles, and it's a repeating customer who purchased more than 5 products. So you can use these attributes to give the best recommendation, the highest price you can probably use, convince the person to buy it. So you can instantly update those models, and every customer can get a different price based on their behavior and their willingness or ability to pay. Also, you are constantly saving the model, and you can use those data to train multiple models at the same time. So now I was speaking about three attributes: the device, the location, the history. But you can also train just a subpart of the model. So for example, just a location and the device. And later you can roll out, or you can use it when you will be adding a third different attribute, like for example the source, where the person came from, if it was another website, PPCs, and so on. So you can have multiple stored models, and you can use them to create new models as well. Okay, now how does it work? So you start with that. They call it in Bayesian statistics. This is called prior, which is your estimate of a good price. And so this is some common price for the product, but actually, as I said, it might be a random number. Now, as I recommend not starting with random numbers, I recommend starting with something that's close to the price you would see in the e-commerce anyway. And on every either sale, when the customer buys, or not sale, the data are fed back to the model, and the model updates its beliefs. So those priors become so-called posterior, so it updates its weights. Those attributes can be of multiple types. It can be categorical, like the type of product or the source where the person came from. Boolean means true or false, or numerical. So it can be, for example, how many products were bought, or and so on. And then the model is updated, and the model has two parts. I will be explaining this in a better detail. I have images, so it might seem difficult at the moment, but I will explain everything. So there are two things: the model itself and something called acquisition function. The model itself, it's here. The thing you see here is the model. So for some, so let's say how many at this price, how many items will be purchased. So those betas, beta 0, beta 1, beta 2, and so on. So what are these? These are so-called, these are distributions, statistical distributions. And this is what this is actually trained in this step. So basically, beta 0 is like a standard distribution. So no matter what is the value, if the customer is using iPhone or Android or whatever, beta 0 is the generic distribution of all customers. So in the middle will be a price that about half of the customer is willing to accept. And then if you go right, higher prices, less customers are willing to accept it. If you go underneath, there will be more and more customers, but your margins will go down because you are selling more products, but your margin are smaller. So actually, there is some point at which, if you multiply your product margin times number of people who purchase it, there is an optimum. So if you had no other thing, if you had no attributes, your model would be mainly this beta 0. It's like the price at which you maximize your total profit on given product. But then you might have additional attributes. So it shouldn't be price. It should be, for example, device, or it could be tree. It's like an index. It might be source. So if the person came from a newsletter and so on. And when you have those betas, each of them, it might be a fixed number potentially, but what you really have, it's also, these are all statistical distributions. So for example, newsletter. So their conversion is better and higher price. And for example, PPCs, their conversion is better and lower price. So actually, by calculating a sum of all of those distributions, you get the distribution for this individual person. And when you look for the maximum margin, this is the price you should more or less suggest. Now, this is, let's say, the model at the moment where you know it. It's the posterior, which means after learning, so the state, which is some curve. And the top, the highest point is your optimum and the best price. But you are constantly learning. You can adjust. You don't know if it is really the highest price. You just like it's your best estimate. So you need to know which price to try next time. And there is another part, the second part in Bayesian optimization, and it's called acquisition function. Acquisition function is a function that looks at your current model, and it looks also, and it's something I haven't been speaking about yet. So it looks at certainty, how certain you are, or the model is about the optimum. And those acquisition functions are balancing two things. At the same time, they want to maximize your profit, your margin with the data you already have, but also they want to minimize uncertainty. So in some time, they suggest to try prices that will maximize your profits. And sometimes those acquisition functions suggest prices that might hide significant improvement in your understanding of your customer price sensitivity. So those models, I will jump a couple of slides forward and then I will come back. So the acquisition function. So when you look at this, these are this is basically the black dots are measurements. The purple line is your expectation. It's a function that describes the behavior of people. And the more measurements you have, if you see those lines, all three, those dotted line, that like let's say lighter purple and darker purple sectors, these are areas of certainty. The wider it is, the more unknown it is. So for example, here, when you look at those places here the model is quite certain about the customer behavior. How will they react to, let's say, prices? Here, you have no data. Here you have no data. The more far you are from your last measurements, the more uncertain you are. So the acquisition function is not only suggesting, okay, the price should be here or here because this is the optimum, but it might try different prices and see like here and here to close the gap and to build learning. And when I was speaking about Bayesian optimization being better than those grids, when you do those grids, you have to do plenty of experiments. As I said, usually it is about 250 measurements for each attribute combination for each product, which might easily take weeks. In Bayesian, 10 times less. So in one day, you might have enough data for any attribute. It depends, of course, on how many orders you have. So the acquisition function is also giving you experiments. So it's not always giving you the optimal price. And you work in certain cycle. So basically, you have a model. And this model gives you the distribution, is the sum of those betas. There is also error. I forgot to speak about error. Like in all machine learning world, in statistics and everything, there is a noise. There is always noise, which means people might be willing to buy it, but in the last moment, their battery on the phone runs out and they can't buy it and they forget. So the price was right, but the people didn't buy it. Or people normally wouldn't buy it, but I don't know, they're drunk. And so they buy it because it's an impulsive purchase. So this is a noise and like this is something that causes, let's say, error. Now, if I will have this model, I can predict like the optimum price at which you are maximizing your profits. But also you have those uncertainties, and then you feed it into acquisition function, and the acquisition function will tell you, try this price, try this price, try this price, which is like we can call it A/B test. It's not like A/B test where you need like A/B test software, but you just need a feature on your website where different customers will get different prices. So it is actually if you have 10 customers at the same time, you have A, B, C, D, E, F, G, H, I, J, K test. Like you are testing 10 different prices at the same time. 10 different prices acquisition function gave you, and then those people either buy or not. And you fit this data into the model. And by the strength of the signal, it is using like the model. It can change the optimal in big steps or smaller steps. So it might, like the distribution here might change a lot. Like when you, for example, see those points that are far from the center line, these actually don't reduce the uncertainty that much. So when you feed it, you are updating the models based on how strong the signal is, for example. You can see that many people are reacting positively at exactly the same price, or people are purchasing with a big range. So the distribution can be highly skewed, or it can be more, let's say, spread out. And it is all used to build those like distributions, and it creates, I would say, a surface. Uh, it creates its surface. It's difficult to explain this because mathematically, like if you had just like, let's say, one attribute or which is price and people's reaction to price, it would be like a line. The line you could see here is the reaction on the price is a line. Actually, it should go down, right? Because the higher the price, the less products people will buy. But when you add another attribute, it's a surface. It's a 3D shape. So, for example, no previous purchases, 1, 2, 3, 5, and so on, going all the way to infinity. The ability or willingness of people to buy things from you might be, for example, slowly getting higher, even if the price is higher. So this creates, let's say, a 3D shape, which is something we still can imagine. But when you add another, let's say, the device, desktop, Android, iPhone, and suddenly we have 4D shape, and on top of that, um, it's something like I think nobody can really like imagine 4D shapes. And if you have 10 attributes, we have 11 dimension shape that's basically representing the willingness of people to pay for your product. And but we still can explain this as an equation, as a model. So the model is basically, these are, let's say, some statistic distributions. So how people react to price, how being returning customer affects it, how if you are selling different products, it might be books, motorcycles, and cosmetics. If it's books, how it usually impacts willingness of people to pay. Those box plots are just simplifications. What it would be is those curves, usually some normal distribution curves around the central price, which maximizes your profitability. Okay, I was already speaking about this. So in that model, it's not just probabilities, but also your certainty, which is important part. Now we will be speaking about another thing. So Bayesian optimization in pricing, it's not like the only thing you need, because you can extend the pricing models, and usually those softwares are trees, decision-making trees, where, for example, Bayesian optimization might be just one part. So you replace the first box. The first box in pricing models is, let's say, 20% fixed margin with Bayesian optimization box. So you feed it with the information about what was the purchase cost of the product, the prior for first learning. So let's say what would be your estimate of the price, and then all the data about those attributes, and you feed it, and you already get an estimate of the optimal price. But then you can combine this with various extensions like buy one, get one free. Subscriptions. For example, when you buy espresso machine, it's one expensive purchase, but then you buy coffee that's cheaper. When you buy an espresso, it's cheaper, but then you have to pay for those cups or those pots, and you are basically paying it back in the subscription. Then you can add various modifications like rounding to 0.99 or 0.95, seasonal pricing, surge pricing, and so on. So you can do it as an extension when you say, okay, when there is too high demand, we will raise the price by 10%. Or alternatively, nothing is stopping you to turn demand into an attribute and train the model, and then Bayesian optimization model can actually give you optimal reaction for, let's say, high demand. And it can give you optimal increase of the price. And of course, this can be integrated into existing e-commerce platforms. How it works is that you take data, order data, and then you have a module like A/B testing module, and you are using this A/B testing module and you push prices into this tool. It does not require any identification of customers. It's compliant with the GDPR. Customers can be completely anonymous, and actually you just aggregate. So you don't have to store anybody's name, address, and so on. So these pricing modules, even when they give people individualized price, they don't have to, let's say, the anonymize. Of course, there are certain ways where you could not, for example, discriminate with price, and it would make it illegal. So of course, when you are choosing attributes, I would pick attributes that are not, let's say, sensitive in any way. So for example, the source where the customer came from, the device, if it's a returning customer, these are no-brainers and good examples. There is another thing. Yes. I will be speaking about intent later. Yes. So how it looks like. So I could run the optimization myself, but basically you would just see the code running and it would be doing a calculation. So what you can see here, for example, it is how it was running. So I trained a model, and here, so we had true optimal price was just over $100, and I trained the model. So initially, It is researching the space a lot. It's jumping all over the place. And then, and it has quite like jumping also margins. But over time, it is learning better and better. But still, the acquisition function is looking around and trying different things until you will find the best price at which your customers are buying. If you run it for even longer, I would probably make the parameters of the acquisition function also to be more variable, and then it will be getting much closer to the optimal price. But you can see like this is real data, how it is finding the optimal price, how it is improving the margin, and how it is modeling where the customer are willing to buy. This is just Bayesian optimization with just one parameter, which is, let's say, sensitivity price. So it is a very simple model that has just one, but beta zero, just reactivity to price and nothing else. Now, there is one more thing I would like to speak about, and it is when you are really using this on e-commerce store, you need to recognize the purchase intent. So for a purchase intent, the problem is if you just feed all the data into the optimization, and it's not just a problem of Bayesian optimization. This will be a problem of every adaptive system for dynamic pricing. If you have people who are coming to your website who don't really have a purchase intent, they like the window shopping. They just like they are thinking of buying a new coffee machine, and they want to see what coffee machines exist, what are the parameters, how the prices look like, but still they need to speak with their partner, whether like how much they want to spend and so on. And they don't really have an intent purchase. They are just researching. And the model is suggesting prices and they don't buy. It is giving the model a signal to lower the price, even when those people did not really have any intent to purchase anything. So you need also to do dynamic pricing if you want to have this feedback loop. If it's just not going to be rule-based decision-making tree that's not using any, let's say, customer data, you need intent recognition. Now, there are existing solutions. Google is selling a solution for about like $50,000 per year. I think MasterCard has a solution for about $35,000 per year, and they are based on cut boost or X boost, which are algorithms to estimate, let's say, categorized gradient boosting, which is also an algorithm that you can use in machine learning, one of the most used algorithms, top 10 in machine learning. So these algorithms are commercially used. Companies are using them and selling them to e-commerce for significant amount of money. I just wanted to show you one thing. I trained Bayesian purchase intent estimator, and I trained also cut boost, which is like what Google is using, MasterCard is using, and so on for purchase intent. And what I found, so the training time was significantly faster. Like this was on 100,000 interactions. It took just 0.026 seconds to train on 100,000 cases. And then, when you are building a model in machine learning, you have training, and then you have something called inference, which is using the model. So first you are feeding it with data, and it is learning, it's updating its weights, and then you save the model, it stops changing, and you do inference. So you feed it with data, and now it gives you answers like the purchase intent, 10%, 90% purchase intent. So cut boost which is now the most used solution in the world, is slightly faster in inference, but significantly slower. When we look at that here, so Bayesian was 15 times faster than CutBoost, but was 1.5 or 60%, 50% slower than CutBoost in inference. The accuracy, achieved accuracy was absolutely like identical, and error rates were identical. So as I said in the beginning of the talk today, Bayesian methods are criminally underused. They are very strong. Like you can quickly get on par with the top solutions used by the biggest players in the market. They are this powerful, and really like there's a lot companies can do with Bayesian optimization, not just pricing or purchase intent. So, so as you can see, for example, here, so I was training on a set that had high intent 0.7, low intent label was 0.07, and this is how close I got with Bayesian optimization. So I got very close in the recognition of the purchase intent. Now, I have also trained more advanced model. Again, I could run it here. It is second. I will just try to just change the sharing for a second. Okay, can you see it? Yeah, I hope so. So basically, I can run it, but I have location, time of day, and number of previous purchases. A lot of data, 100,000 purchases. So when I run it, I'm now simulating, running plenty of simulations with 10 CPU cores, and it's just running. Like there is no point looking at the screen for 1 minute and a half. But what we will get actually, let me just go back to the presentation here, is that over time the error is getting smaller and smaller. So for example, in this round, we started with error like from the optimal price, $3, and over time $2, 1.5. And if I run for long enough, there I will get is actually the level of that error rate. The thing I was speaking about here, so there is always noise. In machine learning, there is always noise. So you never like reach like the optimal price, but you can get closer and closer and closer until you reach basically the noise level. So as you can see, yes, it's already finished the training. Machine learning. I have M1 Pro, M1 Max, MacBook Pro. It is enough to run very fast machine learning on data sets where we have hundreds of thousands of cases. And if you distribute the load to all CPUs, to all cores, you can have a trained model very often in minutes or faster. So as you can see, over time, I was getting closer and closer. Now, how to implement it? So what is common in this space is you somehow track competitors' prices, and you have some historic data, which might include at what price people are buying, how they react to seasons, how they react to discounts, and so on. And you feed this historic data into the model. So you pre-train those models, and once you have them, in your pricing software, you replace the box that just adds the margin with the box that's doing Bayesian optimization. And when you show your website, it shows the price. It takes let's say, a session. So you keep this price consistent for this user session. So if the user will come the same day, the user will get the same price. Next day, you delete all prices, so everybody who will come again might get different prices. So, so this is an easy way. So it becomes a box. And of course, you can enrich it. You can scale it up, down. You can modify it. You can use price bundles and so on. Another thing is you don't need a full-time data scientist. It is not that bad to learn this. If you want it, I can provide some existing solutions. Actually, so yeah, here. Okay. So for example, Bayesian, so simple, quite simple model has 600 lines of code. If we have an enhanced model that has like plenty of improvements, it gets 70% closer to the optimal price, and it has 1,776 lines of code. So we are looking at, let's say, additional 400 rows, but we have a model that's awesome, very close to optimum. I wanted to show you, for example, for intent estimators. So CutBoost is what others are selling. The whole model is like 200 lines, ignoring the documentation. We are looking at, let's say, 160 lines of code, and we have intent estimator Bayesian. Also, when we are looking at that, we are at 180 lines of code, and 180 lines of code, and you have world-class purchase intent estimator. It's not that difficult to build such a thing, and it can be deployed. It can be a good step up for companies who want to just grow from, let's say, more simplistic to more, let's say, well thought and more optimal solutions. Now, I don't want to spam you too much with like any commercial addings, but yes, we have a solution for dynamic pricing. As you can see, we have Bayesian models for pricing. We have builders for pricing strategies. We can import data from Shopify, Magento, WooCommerce, and we can push prices. We are developing also UI for all this, where we will be able to basically drag and drop those decision-making trees. You already have an engine to run decision-making trees, an API. And the good thing is, at certain conditions, we are willing to give all this for free. So you might give a license and not pay anything for that. Now, yes. So this is what we were speaking about. The conditions is we would be those who would be implementing this. I think for every e-commerce company that's over 1,000, let's say, products or over 50 million of revenue under management, it's a no-brainer. It will pay off really quickly.